Welcome to my course Formal Methods for System Verification. So, let us try to understand the course title first. So, the course has the first part is formal methods and for system verification. So, we have to first understand what is mean by system verification and then why do we need formal methods, right. So, in this introductory lecture I will try to cover that first in more detail. So, what is verification, why do we need verification, and then what we verify, and why do we need formal methods for verification and how formal method works, right. So, these are the questions I try to explain throughout this lecture 1 of this course. So, what is verification? So, the definition says the system verification amounts to checking whether a system fulfills the specified qualitative requirements, right. So, it basically ensures there is no flaw in the implementation and the implementation correctly meets the specification, right. So, it basically checks whether whatever you try to implement, it is actually implemented, right. So, whenever you try to implement something, you have certain specification, right, and then based on that requirement or the specification, you make your system. It may be software, it may be hardware, right. So, the verification process checks what you have implemented, exactly implement what you have supposed to implement, right. So, now what is formal verification? Is the mathematical proof method of ensuring a design's implementation matches the specification. So, the verification is checking whether your implementation is correct or not, but you can have different way of checking that, right. So, formal verification is a mathematical way of checking that thing. So, we have understood what is verification. Now, what we try to understand, why do we need to verify, right. So, as I already specified, your objective is to implement certain system and it is done by human being, right. So, there may be some implementation bug introduced during the implementation. You think about a processor design, it is a huge design, right, millions of lines of code implemented by hundred of people, right, and it is not even done concurrently, right. So, there may be some people have developed the earlier legacy part of the processor, which is already they have left the company, joined somewhere else. So, there is nobody is there to tell you what was there exactly, right. There may be some misinterpretation of certain things which was implemented in certain way, and the new persons actually consider that in a different context, right. So, because of all these issues and human error, there are bugs exist in the implementation, and there are actually exist hundreds of bugs, right. So, I have given here two links. I will strongly encourage you to open this link and check. The first one is called common weakness enumeration, which identified many common weakness in both software and hardware, so that when you implement certain things, you make sure that you do not, your system what you are implementing does not have those weakness, right. The second one is bit older link, where it was listed hundred of scenarios because of this bug in your implementation, what was the impact, right. So, I will strongly encourage all of you to just go to this website and see those cases, right. So, I will try to highlight the common weakness enumeration part 1. So, it basically says that it basically lists the commonly developed list of software and hardware weakness that can become vulnerabilities, right. So, if you know these things early, what is impact, you can actually fix it quickly and it's cheaper too. That means cost to fix the bug is less. Why do I say these things? Because if you say developed everything, deployed your product to the customer and they identify the bug, then you have to replace everything, right. So, cost is higher. On the other hand, if you identify that in the early phase of your design and you fix it, your cost will be much lower, right. So, it is very important for every engineer who is developing either software or hardware, or I would say the overall system, they must ensure that their implementation is correct and they are aware of all these common weakness, right. Just to highlight here, I just copy pasted some of this thing from the CWE website. So, you can see that in the software development process, there are many such issues they have identified. For example, it may be authentication issues, maybe bad coding practice, it can be behavioral problem, it can be concurrency issues, it can be cryptographic issues, it may be data integrity issue, it may be data processing issues, file handling issues and so on, right. and if you click on any of them, it will give a very detailed description of the kind of issues and how to resolve that, right. Similarly, in the hardware side, you will see again many issues. The major issues like software security flows issues, maybe integration issues. When you integrate multiple components together, there may be some problem between communicating between two components. It can be privilege issues, access control issues, that is very important in hardware, or it may be problem with compute unit, your memory unit, or maybe peripherals and so on, right. It may be power, clock, thermal issues and so on. So it's very important to make sure that your design is correct, and as a engineer you must visit this and check what is the common issues, right. So it's not only issues, the impact can be catastrophic as well, right. So when you have some bug, it can be costly, right. So just to give you certain examples what I have. So for example, this is a very old one which has, there is a radiation machine for cancer treatment, and there is some overdose of radiation because of some bug, right, and it actually cost in human life, right. So there are 3 cancer patients died because of the overdose of the radiation. And if you look into the problem in this, it's basically some control software bug, right. The software who was implemented, they have not handled the race condition properly. So you can understand, just handling one corner cases probably cost you human life, right. Give you more example, practical example. This is in New York City in back 1990s. Again, there are some outrage in the network channel, and for that, for almost 9 hours there is no network in the telephone network in the entire New York City, and it cost several hundred of dollars, right, millions of dollars. And I want to highlight the problem is that how to so there is some flaw in the software to handle the break statement in C. There may be some scenarios where the break statement was not implemented correctly. So this highlights impact is millions of dollars, but flaw is very simple, right. So some break statement was not written properly, right. Condition under which you should break has not been handled properly. Similarly, it can have a more impact, like there is a crash in this particular European missile in 1996, which also cost the entire development cost, which is more than $500 million. And again, the problem was in the software, control software, and it's basically data conversion from 64-bit floating point value to 16-bit signed integer. Just the way you interpreting data inside, there are some misinterpretation. Because of that, this particular crash happened, right. So again, I try to highlight the bug is not very critical, right. It basically is, we do every day in our coding, right. We try to convert our data from 64-bit to 16-bit and so on, and it's just some problem in that particular conversion that basically triggered something unwanted, right. So the control software probably supposed to do something, it did something else, right. Again, it basically shows that it lacks verification. It could have been verified properly, then this flaw could have been identified early, right. This was the most famous one, Intel Pentium floating point division bug, which is in back 1994. I hope many of you know this. It's basically there was a bug in the Intel floating point division unit, right. So the way you are implementing the division unit in the processor, and it's not a very common bug. The impact was very light, right. It basically in some precision number, right. So when you divide to floating point value, value will be correct, maybe after 4 digits or 5 digits there will be some mismatch, right. So it is not exactly correct, but there are some mismatch in the very lower precision bits, right. And that also not commonly occurring. It's basically, if you do division in this floating point unit of this processor, approximately 1 in 9 billion operation it will occur once, right. It's very hard to detect bug, right. And that's Intel, although have a very strong verification flow, they could not identify this bug, and it was identified by one academic professor in US during his lab research, right. And it cost $500 million to Intel. They have to take it back to all the processor, fix the bug, and then again put it to the customer, right. So this is again it's a very hard bug to detect, but it has been identified by formal verification, right. So this kind of examples will go on, and I would probably try to give you some recent bug in 2023, It is in Google Tensor SOC thermal throttling in it. It's not something serious bug, but the way the thermal management is happening in the TensorFlow, when it have a lot of AI workload, it was not working correctly, right? So again, it's a control logic bug. It was not implemented properly, or all condition may not be handled properly, right? Similarly, again in 2023 in Boeing 787, there was bug in the power control unit. Again, the bug is due to some counter overflow or reset logic, and because of that, in certain condition, the power control unit was disable the generator from continuous operation, right? It's a very serious case. You think about aircraft, because of this bug, some crash might happen, right? So this is again a very common recent bug. Similarly, Apple M series also have similar kind of bug. It's not functional bug, but the security bugs, right? It basically says that there are some data leakage via speculation execution of the Apple silicon. So probably people work on architecture know what is speculative execution, and then because of some data leakage was happening, right, which was bypass the OS level protection. So this actually emphasized that formal verification needed not only to check the functional correctness, also you need for security, right? So you have to make sure that your implementation is secure enough. There is no data leakage or any other such security issues, right? I think the list will go on if I keep speaking, but I think I have motivated enough. Why do we need to verify, right? Because bug can be cost you millions of dollars or maybe human lives as well, right? So then the question asks, what do we verify, right? And probably I have answered that question throughout my discussion so far. It's basically you have the specification and you implement it using manually or using synthesis tools, right? So you have the implementation and you have to check whether your implementation meets your specification requirement, right? So this is what the verification does. Okay. So now the question is, how do we verify, right? So the common way of verification is called simulation based verification. I think we all do whenever we write our C program for lab assignments or anywhere. What we do, we run for some test cases, right? So if we run for few test cases, the output is coming correctly, we assume that we mostly confident the code was written correctly. But the problem with this kind of technique is that for a big system, the combination of input may be quite high, right? Exponentially large with the number of input bit, right? You think about you are doing some operation where there are two input of 32 bits. So effectively you have 64 bits input and number of possible value is 2 to the power 64, right? Ideally, for checking your correctness of your system, you should run for all 2 to the power 64 possible cases, right? Think about your floating point bug that I talked about. To verify that, you ideally have to give all possible combination of input and you have to check the division, right? Then only you can identify such bug. So simulation based verification is good for identifying very obvious bug. If you have some very basic mistake you have done, so that most of the time your output will be wrong, it is good sanity checkers to identify such obvious mistakes in your implementation, right? But when you go for identifying critical bug like the data leakage I talked about in Apple processor, or the floating point bug I talked about, right, or the control statement I talked about, the break statements and all. So for that this simulation may not be good enough, because you will not able to check all possible combinations. It will take ever, right? It's probably 10 years, 20 years to complete your verification, which is not viable, right? So that's why we need formal verification. The interesting part with formal verification is we don't need any test cases, right? We mathematically prove that your system is correctly implemented your specification. So it gives 100% correctness. So people might be very excited, oh, then I will always use formal verification. It has other limitations, right? It is not that much scalable. So you cannot take the entire processor and you model and mathematical equations and you verify whether there is any bug or not. You have to use very interesting strategies so that you can verify the entire system by probably divide the system into small components, verify each component separately, and then combine them together. You abstract out this component and then verify the higher level and so on, right, in a hierarchical way. But this is very important because it is 100% guarantee that if you says that your method is correct by formal verification, it guaranteed that there is no bug in your implementation, right? So that's why this is so important topic in both software industry as well as in hardware industry. So just to emphasize why formal methods give 100% correctness guarantee. So in the simulation verification, if you think about your input space, right? If you think about each dots is basically one possible input, right? In bits input there are 2 to the power possible inputs, right? And those many dots. So if you verify for one scenario, it ensures that for this input there is no bug, for this input there is no bug, for this input there is no bug, and so on. But as I mentioned, there are too many possibilities, so you cannot complete this. On the other hand, in formal verification, you think about in property verification, if you write a property, it ensures that a subset of the inputs cover, and under that scenario there is no bug, right? You write another property that will cover another subset of inputs, you write another property that will cover a subset of inputs. So if you write say probably 10-15 properties, that will cover your entire input space, and it basically ensures that if these properties are satisfied in your system or your implementation, then implementation is correct, right? So this is how just to view the things from a little bit higher level of abstraction, why this formal property verification can cover the all possible input scenarios, because finally at the end you have to prove that if you say that your implementation is correct, means for all possible input your implementation produce the correct output. So even the formal verification has to guarantee that for all possible input your implementation is correct, right? It may be mathematically, it can be using properties, but it has to guarantee that, right? So this particular explanation probably give you this idea that how this property verification can cover your entire input space, right? So the last question is, how do we verify, right? So we probably now understood or kind of accepted that formal verification is necessary. First of all, verification is necessary, and formal verification is important way of verifying your correctness of your system, right? Now I will briefly talk about what are the conventional technique in formal verification which we can verify your system, right? So there are 3 primary way of verifying your system. One is called theorem proving, the other one is called model checking, and the other one is called equivalence checking. Okay, so I'll give you very brief high level idea in the introductory lecture so that you can understand how they work, right? The first one is theorem proving. So you think about that you have a system, right? Think about a Verilog code, right? That's implement your something that you are trying to implement, right? So now you need to model your implementation as a formula, right? So first of all you need to capture your implementation using some formula, okay? And you also may have certain axioms or rules that in this system these are the things should be true, right? So you have to, the formula effectively the theorem prover just check whether the formula or your implementation satisfies under the approximation, right? So just to illustrate this, in theorem proving does not know what your implementation is and all, right? So what it does effectively is it can just take a formula and check whether the formula is satisfiable or not, right? So the term satisfiable I am talking about, right? So what is satisfiable? It means that there exists an input for which the formula is true, right? Whatever the formula that captures your system is true. So that is what the theorem prover does. So now to prove, to check your correctness of your system, what you have to do, you have to model your design or your code into this formula, right? And then you have to use the solvers, right? So whether it can be a SAT solver or it can be a SMT solver based on the theory that you are handling, and then it will just check whether the formula is true for an input or not. There exists an input for which the formula is true or not. And if it is satisfiable, if you model your verification problem such a way that satisfiable means is correct, your implementation is correct, then if you just get the satisfiable, you can actually tell that yeah, my implementation is correct, right? So here the background thing is that you need to model your system into a formula, right? Now how do you do that? You need different logic, right? So there are different kind of logic based on your requirement. So it can be propositional logic, it can be first order logic, it can be first order logic with theories, or higher order logic. So why do we need different kind of logic? This logic has more expressive power, right? Expressive. So it means that if you try to, there are certain things which can be implemented in first order logic but cannot be done in propositional logic, right? There are many scenarios. And similar, there can be something can be modeled in higher order logic but cannot be done in first order logic. So the deep you go, you have more expressive power. But on the other hand, when you deep you go, your checking is becoming more difficult. The satisfactory checking become more difficult, right? So if you in propositional logic, the problem is decidable, right? In higher order logic, the problem is not even decidable. Whether the problem is satisfiable or not, or the formula is satisfiable or not, checking in higher order logic will not be decidable at all, right? So now based on your system, based on your requirement, you can decide which logic you need, and then you have to use the appropriate checking method to check whether the formula is satisfiable or not, right? So no worries, at the start of lecture we'll cover this entire this theorem in more detail. We'll see how we can model a hardware in this logic, maybe in propositional logic, and then we'll go in detail in this course how this SAT solver or SMD solver works, or a given a formula, how you can check whether the formula is satisfiable or not, right? So those things we'll be covering in detail in lectures, okay? On the other hand, model checking is another way of formal verification in which we do in a different way, right? So here we you have the specification or the system, right? You have the specification, you identify the properties, okay? So you need to identify what are the correctness properties, and for that you need temporal logic, okay? It can be linear temporal logic or computational tree logic, right? So it's called LTL or CTL. So we will talk about them again in more detail. So let's say I have those temporal logic through which I can write the properties of my hardware, okay? So from here you implement, right? So you have the synthesis tool and you implement, you have the actual system, and then you model that system also as a maybe state machine, right? Finite state machine. So you need a system model, you cannot just take the actual implementation. And then this properties P, and this is a model, you have to just check whether model satisfy the properties or not, right? It basically means that if the model satisfy the properties, it means your implementation is correct, right? So it will say it is satisfied, or it will say no, and it will give an example or input scenario under which the formula is not satisfiable, right? So this is what the model checker does. So for to understand this model checking or to use this model checking for your verification, you need to learn this LTL, CTL, temporal logic, how to write properties in this logic, and then also you need to understand how this model checking works, right? And obviously you also need to learn how to model a system using a finite state machine, right? So this is what we are going to cover in this course again, right? So we'll teach you what is LTL, CTL, what is model checking algorithm, how to make it scalable, and so all those things, right? So we'll cover all detail in this course. And the last one is called equivalence checking. If you notice here you have a specification and from or as a requirement, and you have the implementation, right? So you do not have two versions of the implementation. You have basically the specification, which may be English language statement that I want this, I do not want that, it should work like this, it should not work like this, and so on. And from there you implement. On the other hand, in the equivalence checking, you have two versions of the implementation, right? You think about, I have a C code and I have a synthesis engine, and it converts this code into Verilog, right, in register transfer level logic. So I have now two versions of the same thing, right? Whatever, if you give the input to C code, the output, if you give the same input to this RTL, it will also give the same output, right? So you have to check whether these two implementations are equivalent or not, right, functionally equivalent or not. Similarly, it can have different strategies, right? So when you do the logic optimization, you have two circuits, right? One is unoptimized, the another is optimized. Again, you have to check whether the unoptimized and optimized is functionally equivalent or not, right? You think about you are converting a RTL level code into gate level code, right. So now you have two circuit, one is register transfer level, the other one is gate level, two different abstraction level, but still they should be functionally equivalent, right. So that kind of checking happen using equivalence checker, right. The equivalence checker inherently use either model checking or theorem proving in the back end, but in a higher level it just do the translation validation, in the sense that you have one version of the code and then another version of the code, and you just check whether this version translates correctly into this version, right. That is what this equivalence checking does. It is also being widely used in the industry, and it's interesting to explore how it works, and we'll obviously we're going to talk about this equivalence checking in this course. Just to motivate you, you should learn formal verification, because if you go any industry, they have more formal verification engineer nowadays than design engineer, right. Just to emphasize that, if you take a very old data, I have taken from courtesy from this company, this is the average number of design engineer versus verification engineer. You can see the verification engineer requirement per design is more than the design engineer, right. It is because your system become more complex, it's become more bigger, more complexities are coming, and you need to make sure that your designs are implemented correctly, right. So this just to highlight that in a ASIC, in the semiconductor industries, you need more verification engineer than design engineer, right. Just to again the design cost, finally when you build your chip, design cost more than millions, right, 500 million, 600 million. And if you see, probably you know this 65 nanometer, 828 nanometer and 5 nanometer, it's basically the size of your transistor. So we are basically heading toward this, and we are currently kind of 5 nanometer, even we have 3 nanometer chip nowadays. So cost is growing when you go for smaller transistors. And if you see here the overall cost to build your chip, majority is in hardware verification and software or system verification. You have very small component of cost coming from IP, right, IP quantification, architecture, right, and then physical in the sense synthesis tools and all, and then probably validations is there, but majority of part of the cost is coming from verification, right. So this is again to highlight that verification is becoming more crucial in the industry. And I don't need to highlight this enough, that semiconductor industries is growing like anything in India, and thanks to our government initiative India Semiconductor Missions, and we are going to have fab in India, both in Gujarat and Guwahati. We are going to see a exponential growth in this domain. We are trying to build chip in India, the in-house chip, starting from specification to the actual fabrication. Everything is going to happen in India, and we need more people into this industry, and as well as you need more formal verification engineer in this growth, right. So again, just to highlight this, verification needs everywhere. This highlight the kind of market we have, and it's across everywhere, right. It is verification market in automotive, consumer electronics, industrial, aerospace and defense, medical, telecom, software, everywhere, right. So you basically have need verification engineer in every domain, right. This is a very important slide. You need to catch your bug as early as possible, right. If your implementation has a bug and if you could not detect it, it will cost you more, right. So this is a very nice diagram I have taken from internet only. If you think about your system development process, you start with say analysis, then conceptual design, then programming, unit testing, system testing, and then you get the operation, right. So if you think about this way, so the most of the bug, right, this is called introduction error, is introduced during programming, right. This is a human error. So most of the bug, 50% of the bug probably get introduced during programming, right, and then it goes down. And the detection mostly happen during system testing, right, verification. So this green line is the detection. So most of the bug getting detected during system testing, and this goes down. And the red one is called the cost, right. So if you identify the cost, detect your bug during programming or testing, your cost is not high, right, maybe 10%. But if you identify this bug during operation, your cost will be very high, right. So this is basically says the sooner you identify the bug, it is better for you, right, in terms of cost. This is again another slide just to highlight where the primary bug comes from, what kind of implementation, and it basically says that most of the cases it is a logical or a functional bug, it's an implementation error, right. 50% time the bug is effectively, and this is basically each bullet is year, right? I am talking about say 2022, so this line. So most of the 50% of your implementation bug is coming from logical or functional bug. It can be coming from clocking, analog device, crosstalk, power consumption, right, reliability, timing, path, so many, right? So it can be safety, security, and so on. So this basically characterize different kind of bugs, right? And most of the bug that I want to highlight is functional bug. It's a implementation mistake. Somebody have not implemented your system correctly, right? So I think I have motivated you enough to learn formal verification, because that's the core thing behind every verification tool. So now there are two ways of looking into this course, right? The first part is that somebody who want to develop such tool, they must know this course, right? So somebody want to work in the EDA industry, verification engineer, verification industry, they must know this logic, how the model checking works or say theorem proving works. Otherwise they will not able to implement things, right? On the other hand, people who are kind of a verification engineer, they want to use this tool to verify the entire system. So they need to know how to write the properties, right? How to model your system, right? So then only they can use this tool. So they also need to know this basic high level formal verification technique. And in my opinion, if somebody even use this model checker or say theorem prover as a black box, if they know the inherent theory inside, they should able to use it better, right? So they will not just do some trial and error. So they know that if I even if I write the property this way, this won't go, this cannot be checked, it will take a lot of time, right? So I should probably do this way so that verification engine can handle it easily, right? So in my opinion, knowing the background of this formal verification, whether it's a SAT solver, whether it's a model checker, or it is other sort of theorem prover, it's very important for every engineer who either develop the tool or use the tool, right? So let me talk about what are the things I'm going to cover in this course. First week I'll talk about what kind of different formal methods we have, how to verify. I'll probably take case studies to show you that, oh, this is how you can model a problem into theorem proving, this is how you can model the problem as a model checking, this is how you can model the problem as a equivalence checking, and so on, right? And then first part of the course I'll talk about the theorem proving part, where I'll review different logic I talked about, right? Proposition logic, predicate calculus, higher order logic, right? Then I go into more detail about these solvers. Primarily I'll cover SAT solver in this course, where how this given a formula in say proposition logic, how do I check whether the formula is satisfiable or not, right? What is the internal algorithm, how the algorithm works, what is there inside this tool, right? So those will go in detail, and I think it will be very useful. We'll also talk about the BDD and other techniques, how to model the hardware in binary descent diagrams. That is also I'll cover in the first part of the course. Second part of the course primarily focused on formal property verification, which is basically model checking, where I'll introduce all the temporal logic like LTL and CTL, and I'll see how to write properties in CTL and LTL, and most importantly how their model checking algorithm works, right? How internally a LTL property will be checked, or how a CTL property will be checked inside this tool, right? And then this is very well known problem, that state explosion problem, and how it is being handled using inside the tool by symbolic data structure, symbolic model checking algorithm, and bounded model checking, right? So these are the things I'm going to cover in formal property verification, and this is one of the hot area now. Every industry is looking into this, that how this AI aided verification works, right? Can I use LLM to generate my properties for the designs? Can LLM or some ML technique assist the SAT solver to quickly decide whether the property is satisfiable or not? I think these are very important topic, and people are looking into this so that overall verification time can be reduced, right? So I am also going to cover that part in this course, and I'll specifically want to highlight that I'll take case studies from hardware industries. I'll take certain design, I'll show you how to verify this, what will be the process to be followed in the verification steps. So the early design engineer, the students who are not so sure, they will get an idea how to go ahead in the verification process, right? These are the two primary book I am going to follow. This book I will follow for this formal, the first part of the course, where I will talk about the SAT solvers, and this book I will cover primarily for the model checking part, right? Logic in computer science. In this course I am going to mostly the model checking part I will cover from this, and some of the logic part I will cover from Manna's book, and LTL property I will take from this book, right. So, these are the primary book I am going to follow in this course. Somebody who is a very serious learner can buy these first two books and learn more detail, but I think the video lecture will be good enough reference. To conclude, the verification is so important and it has been awarded. The three eminent researchers who developed this model checking algorithm, they got the Turing Award in 2007 for their developing this model checking into a highly effective verification methodology, right, widely adopted in hardware and software industries. So, I think this should be a good enough advertisement that verification is very important in both software and hardware industries, and I am sure this course will be very much useful for you, and with this course you have the enough knowledge in verification so that you can apply this both in software and hardware industries. Thank you. Looking forward your active participation in the course.